Okay, so chapter one you can think of as more of a general science chapter, just kind of building the foundation for what we're going to be doing going forward with the rest of the Gen Chem sequence. So now with chapter two, we're going to start to really dive more into the chemistry specific kind of material. With some of this, especially atoms and molecules, compounds, things like that, we touched on in the first chapter, but we'll go deeper into that as well as look at some other new aspects of kind of the foundations of matter and how we understand the atom to be. Um, and a long time ago, so 5th century BC, there was two Greek philosophers, Democritus and somebody else. But they hypothesized that matter, so everything around us, remember, matter is anything that's takes up space and has mass. So pretty much anything tangible. But matter was composed of indivisible small particles called atomos. So you can kind of see where the term atom comes from right there. We're just dropping that second O. Um, and with it, as we go through the sort of the evolution of the atomic theory, because with science in general, proof itself is going to be really difficult to um, actually establish or reach. So what we do is just collect as much data as possible, analyze that data, and then come up with a conclusion based on that data. But if we ever get some new piece of information, then we have to kind of adjust our way of thinking, our understanding of the world. Um, but these philosophers thought of matter kind of as just tiny particles, and then once we get down to those particles, we can't break it down any further. So if you think about just like a piece of paper, if we just think of that as one pure element, we could rip the piece of paper in half. We could then rip that in half, and so on and so forth. And then eventually we would get to a point where we had two atoms left. We could rip those in half and just be left with one. But the indivisible piece means once we get down to that individual atom, we can't break it down any further. That's just the smallest thing we have. Um, and then Aristotle, I don't know actually when Aristotle lived, but sometime after that, came up with his thinking of matter, and it's going to be the four elements. So if you think kind of like Avatar, earth, wind, fire, and water. And with this idea, it was infinitely divisible, so we could always take it into a smaller amount. And then this belief actually held until John Dalton. So he's a British scientist. I think he was British at least. Came up with his atomic theory. So there's going to be kind of 5 different rules that we'll go through. So the fifth one just on the next slide. But some of these we've already kind of talked about. And then with this, we'll also see it's not perfect. So there's still going to be changes because with this Dalton's theory, you can kind of see here. This is how we'll typically on the right-hand side throughout the sequence kind of just show atoms a lot of the times, just as sort of these spheres, just because it's easy to show them together. But what Dalton kind of thought of is the atom as sort of a billiard ball. So this actually does a pretty good job of representing his concept. But just to go through these different rules, matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change. Um, and I think if you've taken any sort of general science class and just briefly even touched on chemistry, you've probably heard a definition similar to this. We talked about it a little bit in the first chapter as well. But then going on to the second one, an element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of the element. And then on a macroscopic sample, an element contains an incredibly large number of atoms, all of which have identical chemical properties. So if we just think about these first 2 rules, essentially it's just saying everything's made up of atoms. Atoms are the smallest particles that we have. So kind of similar to what the Greek philosophers believed. And then the atom is going to be the piece that's actually participating in those chemical reactions. And if we think about something like a penny here made of copper, there's going to be an incredibly large number of atoms in that penny, just because the atoms themselves are unfathomably small. With this second one, though, you might want to put an asterisk next to it, because with this sort of the middle or the ending of that first sentence, a mass that is characteristic of that element and is the same for all atoms of that element, we'll actually see throughout this chapter that that's not true. And you may already be familiar with that yourself. So if you've ever heard of like carbon dating, uses two different versions of carbon, and the chemical properties part is the same, but the mass of those is going to be different. Or uranium for like nuclear energy, nuclear weapons. There's uranium-235, uranium-238, both uranium, but they have different masses. And that actually is why we can only use one of them in those nuclear processes. But then with the third one, atoms of one element, different properties from atoms of the other element. So as we start to look at the periodic table itself a little later in this chapter and into the third one, we'll see exactly why it's set up the way it is, because there's going to be elements that'll behave similarly to one another. But there are going to be differences between those. So this is essentially just saying copper is different than oxygen, it's different than nitrogen, is different than helium, is different than any of the other elements on the periodic table. And then a compound consists of atoms of two or more elements combined in small whole number ratios. So we'll see this more in the next couple slides, because we're going to have different rules for kind of the ratio of elements to one another. But just remember from the previous chapter, molecules are any collection of atoms or any combination of atoms. Doesn't matter if the same atom or different. So we could have things like oxygen, two oxygen atoms together, or we could have something like water, two hydrogens and an oxygen. And in both cases, those would be molecules because they're a collection of atoms. But only water would be considered a compound because it's two different types of atoms. So in that case, we've got hydrogen with oxygen. But with water, H2O, it's always going to be that exact same thing. If we had some different ratio, so if we had H2O2, we add on an extra oxygen there. It's no longer water. Now it's hydrogen peroxide. Still a compound, it's just a completely different one because we no longer have those elements in the same ratio, same combination. And then finally, this fifth point just describing the law of conservation of mass. So when we start to look at chemical reactions, we're going to be taking the atoms we have and just rearranging them differently. So we'll break bonds, we'll form new bonds, create new substances ultimately, but we're not going to be creating or destroying anything about the atoms that we actually have there. So if you look at the picture here, you can think of on the left-hand side that bottle, and then notice we've got a cap on there. So nothing's going to be going into the bottle, nothing's going to be coming out of it, but we've got a sample of copper at the bottom, and then the air in there is going to be oxygen. So those red circles are our oxygen, the brownish ones are copper. And then we can have a reaction take place where we now are mixing those together. Now we've got copper to oxide. And that's why you can see the substance itself has gone from kind of that brown, rusty color for the metal just to sort of a black powder. But if we were actually to look at the atoms themselves in both of these samples, including the air in the bottle, we'll have the same number of oxygen atoms overall, we'll have the same number of copper atoms overall. It's just we've taken them and rearranged some of them. There may still be oxygen left in the air. There could potentially even just be a little pure copper left as well. But we've definitely had some reaction take place, and we haven't created or destroyed anything about the atoms we started with. But like I said, with compounds, we always have those elements in the same ratio. If we had them in some different ratio, it's just some different substance. And that's going to be true when we're looking at multiple samples of a substance. So we could think about taking 3 samples, A, B, and C here, from 3 different bottles of isooctane. So it's just going to be an organic compound. But we could get isooctane from 3 different bottles, get the mass of carbon in that sample, get the mass of hydrogen in that sample, or we could get isooctane from 3 different countries. So we could do it here in Washington, we could go somewhere in Asia, somewhere in Europe, Africa, wherever. And if it's isooctane, regardless of how much of that sample we actually have, because you can see in all three of these cases, we've got a different amount of carbon, different amount of hydrogen. But no matter what, the ratio of those two elements to one another, if it's isooctane, is going to be exactly the same. So that's why when we look at the right-hand side here, 5.33 grams carbon per 1 gram of hydrogen, because in this substance, that's going to be the exact ratio we have. So it doesn't matter if we've got almost 15 grams of carbon or over 22, almost 20. We've got a different amount of hydrogen that's going to match up with that as well. So because we're always going to have the same number of carbon and hydrogen together, we're always going to have that same ratio regardless of the sample. And with this, I'll typically call it constant composition, but I just put parentheses there for definite proportions. Means the exact same thing, but I just put it there because the textbook also uses that term. But just because we've got the same two elements doesn't necessarily mean we've got the same substance. And we can see that here with a copper and chlorine compound. So you can think of the brown as the copper still, and then the green is going to be the chlorine. But when we're looking at this, we can see if we were to take the ratio of those elements to one another in each of these samples, so we can see just based on the images that they look quite different. So we've got a green sample here, we've got a brown sample here. So if we were actually to take the ratio of copper to chlorine in each of those, you can see on the top, we've got kind of two fractions within another fraction. So if we just focus on the top here, 1.116 over 1, we've got 1.116 grams of chlorine for every gram of copper. Whereas in the other compound, we still have for every 1 gram of copper, but we've only got 0.558 grams of chlorine in this case. So when we do that division, if we think about 1 gram of copper is going to cancel. So we're just going to be left with 1.116 over 0.558. So we wind up with a ratio of 2 to 1. What that's telling us then in this top compound, we're going to have 2 of those chlorines for every 1 of the coppers. And that's why we've got these 2 different substances now. We've got chlorine and copper in 2 different ratios. So even though they're the same elements combined, we don't have them in the same ratios. They're 2 entirely different substances. That would be, again, the same thing if we looked at H2O water versus H2O2 hydrogen peroxide. We'd see a similar thing if we looked at carbon monoxide versus carbon dioxide. Dioxide is going to have that second oxygen there. So again, the same elements are combined, but we've got them in different ratios. So if we look at the ratio of these 2 together, and they happen to be the same, if this was also 1.116 on the bottom, or 0.558 on top, then we'd have them in the same ratio. They'd be the same substance. But because we do have copper and chlorine combined in different ratios, we just have 2 different substances. And that's why if you look at the images here with the atoms kind of drawn, the first one, we've got 1 copper for every chlorine. So this would be the 1 to 1. And then in this case, now we've got a second chlorine for every 1 copper. So we've got 6 coppers total here, but we've got 12 chlorines overall. So we've got a 1 to 2 ratio versus a 1 to 1. So if we look at a practice one, and we'll see another one after this as well, a sample of compound A, clear colorless gas, is analyzed and found to contain 4.27 grams carbon and 5.69 grams of oxygen. A sample of compound B, also clear colorless gas, is analyzed and found to contain 5.19 grams carbon and 13.84 grams of oxygen. Are these data an example of the law of definite proportions, which is also just the law of constant composition, remember? The law of multiple proportions, or neither? And then also, what do these data tell you about substances A and B? So again, in each case, we can't just use the physical properties to determine what these are, because we've got 2 clear colorless gases. So they may be the same, they may be different. That's why we want to focus on the ratio of carbon to oxygen. And with this one, just quickly looking at it, if you see, we've got 4.27 grams of carbon in our A sample, 5.19 grams of carbon in our B sample. So we've only got a little more carbon in the second one. But then when we look at the oxygen, 5.69 grams to 13.84 grams. So if we quickly just look at those numbers, we can see that we've got a lot more oxygen in the second one. So we've only got a little bit of an increase from carbon, but then the oxygen more than doubles. So to me, that's an indicator that these likely aren't the same substances. Again, we've got the same elements combined, but we've got them in a different ratio, just quickly looking at it. But in order to get more of the detail, we can take the ratio of both of them. So for the first one, we'll divide 5.69 grams of oxygen by 4.27 grams of carbon. And the way I would do it is just always put whatever element you have more of on top, just so you get a whole number rather than like 0.0 whatever. But it doesn't actually matter as long as you keep the order of those be the same for both of them. So if I take oxygen over carbon for sample A, I just want to do the same thing for sample B. So I'll do 13.84 grams of oxygen over 5.19 grams of carbon. And when we do that, we get two different ratios in this case. So for sample A, 1.33 grams over 1 gram, and then 2.67 over 1. So we can see these are different ratios. So these are going to be different substances. And then if we take those ratios and just divide them together, so you can see it down at the bottom here. Again, 1 gram of carbon, the same in each case, so that's going to cancel. So we really just have 1.33 over 2.67. And if you wanted to, you could take those ratios reversed as well. In that case, it would just be the ratio of B to A rather than A to B. But it's the exact same thing. So the order doesn't matter how you plug these in terms of the individual ratios, as long as you keep them the same for both compounds. So again, oxygen over carbon. And then when we're comparing those ratios themselves at the bottom here, also doesn't matter which order we put those in. We just want to recognize that if we're trying to determine like an actual formula at the bottom here, we understand which ones represent which. But when we divide those two ratios together, we get 1 over 2, telling us we have 2 oxygens in sample or compound B for every 1 oxygen in compound A. So one possible, and we could have other ones, but one possible solution for that then would be the formulas for carbon monoxide for A and carbon dioxide for B. But at this point, all we know is that we've got 2 oxygens for every 1 oxygen. 2 oxygens in B, I should say, for every 1 oxygen in A. So we could have CO and CO2, or we could just have oxygen in any absolute number. So we could have 3 and 6, we could have 4 and 8, we could have whatever it's going to be. We just know at this point, since it's simply just the ratio, we'll have a extra oxygen in B. So if you want to practice with this one on your own, it's going to be kind of the same idea. A sample of compound X, clear, colorless, combustible liquid with a noticeable odor, is analyzed and found to contain 14.13 grams carbon and 2.96 grams hydrogen. A sample of compound Y with very similar descriptions, although a slightly different odor, is analyzed and found to contain 19.91 grams carbon and 3.34 grams hydrogen. And again, the questions are the same. Are these an example of definite proportions, multiple proportions, or neither? And what do these data tell you about substances X and Y? So we can do the same thing, take the ratio of each of those. So I would do 14.13 grams of carbon over 2.96 grams of hydrogen for the first one. And then the same thing, 19.91 grams carbon over 3.34 grams hydrogen. And ultimately, that first ratio is just going to come out to 4.77 grams of carbon per 1 gram of hydrogen. And the second one will come out to 5.96 grams of hydrogen, or of carbon over 1 gram of hydrogen. So since those are different ratios, indicates this is going to be a different substance. And then when we take those ratios and divide them, we'll get 0.8. So if you did it the opposite way, if you just had substance B, or I guess X and Y in this case. So if you had substance Y on the top and compound X on the bottom, then you'd wind up with 1.25. So you'd wind up with 5/4. But it would still be the same idea since we're getting whole number ratios here. This is going to be the law of multiple proportions, same elements, just different ratios. And that's why we're indicating X and Y are different substances here. And we'll have 5 carbons for every 4 carbons when we look at Y versus X, just based on that ratio. It doesn't necessarily mean we have 5 carbons and 4 carbons. It just means that ratio is going to be 5/4. Okay, and then with the evolution of the atom, like I said, as we get better understanding, we get more information, we improve our model of the atom, and you can kind of see that progression throughout. And what we're going to be doing is primarily focusing on, at least for the rest of this section of the chapter, kind of focusing on the middle here, J.J. Thomson, Ernest Rutherford, excuse me. But I just noticed I took this image offline. All matter is composed of small invisible particles called atoms. That should be indivisible. But you can see Dalton and Democritus pretty similar. Both of those are just kind of, yeah, and then the same thing here. I really should have checked this. I assume whoever would spend time making something like this would be able to have the correct word there, but that should be indivisible. But when we're thinking about the atom up to this point, Dalton is how far we've gotten. Again, we're kind of just thinking about it as a billiard ball. Each element is a different type of billiard ball with its own properties. And those are going to be the smallest things that we have. But what we're going to see is with the experiments we'll look at here, we were able to discover the subatomic particles, so the things that actually make up an atom. We're going to have 3 of them: an electron, the first one here, the negative subatomic particle, the proton, the positive one, and then the neutron, which will just be neutral. And with the discovery of the electron, which also sort of implied the discovery of the proton, we'll see exactly why. That was discovered by J.J. Thomson. So with each of these different parts, I've just got a video here for Tyler DeWitt. So you can see Tyler DeWitt here makes a whole ton of YouTube videos. I think they're extremely helpful, and I think he does a good job kind of showing whatever that topic may be. He's always got the camera from above, and you can kind of see how he moves the paper around, because he's got different pieces to go with it, exactly what's happening there. So I'd recommend kind of watching that one and the same thing. Oops, I did not want to actually play it. Oops, and I didn't put a picture in there.
In this video.
Yeah, I didn't want to actually play this. I don't know how to get that or not.
We're going to talk about how.
Okay, so just looking at the picture here, I thought I actually put this on the next slide, but I guess not. What he has is a cathode ray tube. So it's a glass tube that essentially just doesn't have air in it. And then there's 2 pieces of metal. So you can see one here has a hole in the middle. There's another one that his arm is covering that just doesn't have a hole at all. But they're hooked up to a power source. And you can see the positive terminal here. The negative terminal is just going to be right here. And by turning that on, you create the current. And then, whoops, what actually,
In this video.
sorry. What actually happened occurring was you'd see a glowing light being produced at the end here, because there was a special coating on this cathode ray tube. And the reason the beam kind of went through is because we have that hole in the second piece of metal, but these particles are moving so fast and they're attracted to the positive end just because the negative ends on the other side. But they're moving so fast, they would just continue through that hole in the second piece of metal. And then in order to kind of understand the properties of whatever was being produced there, because they didn't know what those things were, they didn't know what that beam was. J.J. Thomson put charges around it. So you can see in this case a positive charge up top, a negative charge on the bottom. And what actually happened to occur was, since the beam itself here, again, was the discovery of the electron, so this is going to be a negatively charged beam. Since it's negatively charged, it would actually curve up towards the positive plate. Or you can think about it be repelled by the negative one. Remember, like charges repel, opposite charges attract. So this negative beam is going to be attracted to the positive side. So he saw it curve up. And then he replaced the charges here with just a magnet. So you can kind of think of that horseshoe magnet, kind of just wrapped around the cathode ray tube. And the magnet itself affects the particles as well. It caused the particles to go down, which is what he expected to see here if the charge on the beam was negative. So based on those results, they determined that the beam itself was negative, and then based on the amount that the beam of light curved with the magnet, they were able to do a series of calculations to determine the mass of the particles that were being shot out. And what they found is that the particles were much, much smaller than the mass of a hydrogen atom. So we'll learn hydrogen atoms are our smallest atoms. But if these particles were even smaller than a hydrogen atom, that means there's something below the atomic level. And that's why we refer to them as subatomic particles. So if you just think about kind of the breakdown of that word, atomic, just referring to atom, but sub meaning below. So below the atomic scale, if you think about subterranean, is below Earth, because Terra just refers to Earth. So subatomic just means smaller than the atomic scale, because these particles are going to be extremely tiny, even compared to atoms themselves. So they're going to be thousands of times smaller. And then also with this, since they discovered the negative electron, they still didn't know how the atom kind of was shaped, but because they discovered the negative electron, and atoms themselves are typically neutral. Like I said earlier, this implied the discovery of the proton, because if they knew there was this negative piece with the electron, they knew there had to be some sort of positive piece as well to balance it out in order for the atom itself to be neutral overall. So because they discovered the electron, they knew that there was a proton. They didn't know exactly what it was or how it worked, but they knew that it was there. And that's why if we go back here, we can see J.J. Thomson's model after that discovery, the plum pudding model. So plum pudding, just a British dessert where it's just kind of like, I think it's just like cake or something with like plums just scattered about. So you can think of the atom itself as kind of the cake and the electrons as the plums, because with this model, they just assumed the atom itself was positive, but then it had the negative electrons just sort of embedded and scattered throughout. And like I said, I would recommend watching this video because he does do a good job showing kind of how all of those pieces came together. Oops. And then the next experiment, still focused on the electron, help us determine the charge on an electron. So at this point, if you think about it, we know the mass of an electron. We know that electrons are negative, but we don't know exactly how negative are they. So we have this experiment known as Millikan's oil drop experiment. And the way it works is they have oil in this atomizer. So you can see they spray it into this chamber. And then we get very fine droplets. And some of those droplets just ionize themselves. Sometimes there's the X-ray to help produce a charge on those droplets. But either way, we're going to wind up with these droplets becoming positively charged, meaning they lost electrons. So if an electron is negative and we lose an electron, we're losing a negative charge, becoming more positive. But we spray the droplets, they become positive, And then there's this tiny hole that allows a droplet to sink through. And because these droplets are so tiny, there is a microscope basically hooked up so that the scientist can observe that droplet fall. And if we just think about gravity, anything we toss up is eventually going to come down. So the droplets themselves are just going to fall based on gravity. But because they're charged particles, what we can do is use electrically charged plates to kind of balance out that gravity. And with this one, I actually think the textbook, so this is where this image comes from, I think the textbook has this wrong. I think the negative plate should be on top, the positive plate should be on the bottom, because like I said, these droplets themselves are losing electrons, so they're becoming positive. If we had the positive plate on top, that would push the droplet down. Gravity's already pulling the droplet down, so we would have both of those forces pushing the electron down. But if we switch these charges, if we have the positive one on the bottom now we have that positive charge, or we can think about we have the negative on top attracting it. We're going to have the electric charge pulling upwards, gravity pulling down. So what the scientists can do in that case is essentially change the power on these plates in order to balance gravity. And then because they have the eyepiece, they can see how that's working. So they can turn the charge up, they can turn it down, whatever it may be, till they actually get that balance. And at that point, we've got the charge of, or we've got the force from the charge, we've got the force from gravity balancing out. And because they know the mass of or they can measure the mass of the droplet, they can figure out that force of gravity. And then in terms of the force of the electric plates, they know what the charge on the plates is. So they can figure out the charge on the drop. And then what they did was look at the charges that they were measuring there. So you can see 4.8 times 10 to the 19, 3.2, 1.6. They measured all these charges and then noticed that they were all a multiple of the charge we're seeing down here in category, or with sample D or drop D, 1.6 times 10 to the 19th. So because every charge they were measuring was a multiple of this value, that indicates that the charge of an electron is just this number. You can kind of think of it as the fundamental charge of an electron, whereas with these ones now we'd have 2 electrons or 3 electrons in A, 4 electrons in C. But they were able to determine the charge on just a single electron. But remember, the charge that they were measuring on the drop itself was positive. So that's why these values are positive. The electron would then just be the negative value. So an electron, we're going to say, has a negative 1.6 times 10 to the 19th coulombs charge on it. And then again with this one, he's got a good video that kind of shows that. So if you want to see, the forces, so the actual vectors kind of drawn out, he does a terrific job with that. And then he also has the positive plate on the bottom. So that's again why I'm saying the textbook image here is incorrect. If we had the positive charge on top, we'd be pushing the positive particle down, or positive droplet down. So there'd be no force trying to pull it up. So at this point, we now know the charge of an electron. We know the mass of an electron, and you don't need to memorize those, but just to put in perspective how small those electrons actually are. The mass is 9.1 times 10 to the negative 31. So if we think about this value in standard notation, we would really have 0 point and then 30 zeros, and then finally a 9. So it's an unfathomably small number. And the charge is almost equally as small. And we're actually going to wind up using just basically -1 to represent the charge to keep it easy. But this is just the charge in coulombs. And then again, you can see this was Thomson's kind of idea of the atom. Positive sphere with just the negative charges embedded throughout. And then Hontaro Nagaka I can't pronounce that last name. I've only actually read it, but I know however I'm pronouncing it is not correct. But he was a Japanese scientist. He came up with, in the turn of the century, or I guess last, so early 1900s, he came up with his own sort of, because he was an atomic scientist as well, came up with his own theory of the atom. And you can see it's kind of similar in the sense that we have this positively charged piece, this sphere, but instead of having the negative charge embedded throughout that, he had the negative charge, just like Saturn's ring. He just had the negative charge kind of orbiting the atom itself. And we'll ultimately see neither of these are correct, but we'll see this example with the ring is going to be closer. And with this next experiment, so this is going to be Rutherford's gold foil experiment, he utilized alpha particles. And we haven't covered what the symbols at the bottom represent yet. If you've taken an intro chem class before high school, you might be familiar with those. But essentially what this is showing is, instead of a chemical reaction, it's showing a nuclear reaction. So like I mentioned earlier with the law of conservation of mass, chemical reactions, we're just taking those atoms, rearranging them into something new. With these nuclear reactions, we're actually changing what those atoms are. So in the case of the reaction down here, this is going to be the source of alpha particles for this upcoming experiment. So they can take a radioactive radium. So radium-226. 226 is just the mass of that isotope, or that specific kind of radium. But because it's radioactive, it's going to break down into radon and then an alpha particle. So we'll ultimately see an alpha particle is just a helium nucleus. So 2 protons and 2 neutrons. But again, I just wanted to go over this because the alpha particles are going to be an important piece of this next experiment, which gives us a really good understanding of kind of the setup of an atom overall. But just looking at this reaction closely, radon, I don't believe it's too big of an issue in Washington, but I know in Utah, for example, it is. Places that have a lot of uranium in the soil, ultimately that uranium will break down into radon through a series of similar types of reactions as we see here. But radon is going to be a gas, and these alpha particles, these helium nuclei, are a type of radiation. But with the alpha particle themselves, they're relatively large, so they don't have a very high penetrating ability. So even just a piece of paper can stop a helium particle, or an alpha particle, excuse me. Your skin is enough to stop an alpha particle. So if the alpha particles are on the outside, they're not problematic really. But with radon, it becomes a gas. So then if you breathe in that radon, it'll ultimately undergo a similar type of decay where it then releases an alpha particle. And once that alpha particle is inside, then it can start causing damage to the cells that it comes in contact with. So that's going to be one of the reasons radon, depending on exactly where you live in the country, radon is something that you may or may not need to really monitor in your home. Because you just want to make sure that the concentration of that gas isn't getting to a dangerous level. But like I said, with Washington, I don't believe it's an issue at all. It's usually, from my understanding, the kind of the Rocky Mountain states sometimes have it worse. But with the experiment here, we've got Rutherford's gold foil experiment, excuse me. So we've got this radium source that's going to essentially shoot out the alpha particles in a beam. And then the gold foil experiment, we've just got a very thin piece of gold foil. And then it's surrounded by a detector that can tell where those alpha particles are kind of hitting. And if you look, we see this beam of alpha particles. And then we've got a similar beam on the other side of the gold foil, because most of these alpha particles are just passing straight through. And with that, that's going to lead to one conclusion about the atom. But then we see a few points scattered kind of off to the sides a little bit. We see a few points that were basically deflected straight back. And those are also going to give us some information about the way the atom is structured. So with the particles that go straight through, we think about what that represents. In order for it to go straight through, that means there would have to be nothing there. So because most of these particles pretty much just pass through unaffected, that tells us that the atom, or the volume that an atom occupies, is actually going to be mostly empty space. So if we're thinking about just one individual atom, there's not really much there. But then because we've also got a handful of alpha particles being scattered off to the side, we've got a few, not a lot, but even less than we had scattered, but we've got a few that get deflected back. That tells us that not only is the atom mostly empty space, but there's going to be a very dense positive piece in the middle, because these alpha particles, I should have mentioned explicitly, but these alpha particles are just going to be positively charged. So if we bring them near another positive charge, they're going to repel. So the reason most of them get scattered off to the side is because the positive charge in the atom is going to be very, very small in terms of sort of where it's located. So we're going to have a lot of empty space, and then just a very dense, small positive nucleus. So when the alpha particles get close enough to that nucleus, most of them just get repelled off to the side, so they kind of just angle off a little bit rather than just passing straight through. But every once in a while, if you think about it, if we had a alpha particle kind of approach that nucleus straight on, that's where we're going to see it's going to get deflected kind of straight back. Because in that case, the charge isn't just going to sort of gently push it off to the side, it's going to force it back in the direction in which it came. So when we're thinking about the atom as a whole, what this is telling us is that the volume, like I said, of an atom is mostly empty space, and the atoms themselves have what we call a nucleus, which is going to be a very dense, relatively dense, I should say, compared to the rest of the atom. That's where essentially all the mass of the atom is going to be located, but it's also going to be a positive charge. So if we just think about this atom as one of the atoms in that gold foil, you can see most of this is empty space within this circle. So most of the alpha particles are just going to kind of pass right through. Every once in a while, we might get one that comes kind of close to the nucleus, so it might kind of be coming through at this point. But because it's going to have that positive charge as well, it interacts with the nucleus and then just kind of gets pushed off to the side, or we could see the same thing over here. But every once in a while, we'll have a positive charge that's coming directly at that positive nucleus. And then because those charges are going to repel, we then see that positive charge kind of get shot directly back. And then additional experiments were performed that ultimately led to the protons in the nucleus. So rather than just one big positive charge here, we've got individual subatomic particles, so individual protons. So instead of thinking of this as one big circle, we could think of it as several tinier positives. Excuse me. Okay. And then with the final piece, probably the most difficult to actually discover, because with the previous two, the proton and the electron, both of those have a charge, positive for proton, negative for electron. But when they were looking at atoms, they noticed that not everything kind of matched up with what you'd expect if it was only the protons and the neutrons. So hydrogen and helium, for instance, are our first two elements. Hydrogen with one proton, helium with two. And if you could take multiple of those atoms, you would think, if it's just protons and electrons, since helium has two protons and hydrogen only has one, you would think two hydrogens would balance out one helium. But what they noticed is it actually took 4 hydrogens to balance out that 1 helium. So they realized there was a missing piece in terms of the mass of these atoms. So James Chadwick set up an experiment kind of similar to that gold foil one. So you can see we've got another source of alpha particles. We're going to direct them at a target. But in this case, you can see that target's going to be beryllium or boron, so just other elements, pretty light elements, because those are going to be the 4th and 5th element. So it's skipping lithium, but I think lithium was also used in this. But I'd have to double check that. But we've got this source of alpha particles, and we're going to hit the sheet of either beryllium or boron. And then what they noticed is that there was some beam essentially coming out. They didn't know what it was, so then they had a paraffin sheet, so just kind of wax, that the beam would hit, and then from that point they noticed protons were being ejected. So initially they thought that this might be gamma rays, just a particular type of radiation, this middle piece right here. But if it was gamma rays, the gamma rays themselves wouldn't have the mass necessary to eject the protons. So what they realized was that these beams that were being created after the beryllium or the boron was hit had to have a mass similar to the proton. And that's where the discovery of the neutron came from. And again, with this one, if you want to go through, he goes in a little bit more detail there. And again, I just like the way that he has the paper set up. You can see kind of how different pieces of those experiments came together, as well as a little bit of background to it. So I'll put all 3 of those videos for the different experiments in that course playlist. Oops. But that'll be where we wrap up the first section of this chapter. So with the next piece, we'll start to actually look at more of the exact structure of the atom, and then more into the different pieces of those, so the electron, proton, neutron, and how did the number of those determine what type of element we have, what type of properties that element's going to have.